our sponsors. And it looks like the wired mic up here is working just fine, so hopefully you'll be fine.
All right, good afternoon, everyone. I'm Bob Richards. I'm from the U.S. office of TT Tech, and myself and Matt Sweeney are going to be giving you an overview of how the TTE tools and products are going to be used to support the gateway. So TT Tech supports many different industries: automotive, factory automation, civil aviation including flight controls and fault-tolerant subsystems, et cetera. But my emphasis is on the space. I lead the space activities in the U.S. here, and you know, human space flight, as we've talked about in this conference, the Artemis program, the Gateway, is really a national priority, and NASA has set open standards for the Gateway. And those open standards include time-triggered Ethernet and other things which TT Tech will definitely be supporting. So if you, let's see, I guess I've got the clicker. So today we're going to just give you a quick overview of you know, what the Gateway is shaping up with for data backbone products, and then how some of the TT Tech products can be used to support the time-triggered Ethernet data backbone at Gateway, and also a little bit about our development environments and how we think that application software could be developed on these development systems to be most efficient and take advantage of the capabilities of the TT Tech products. So Gateway is still in formulation, but you know, one thing's for sure, it's a 3-lane data backbone, and it's a switch-based system using time-triggered Ethernet. The exact number of switches, the exact number of end systems is still in, you know, design, and we're supporting the various prime contractors and NASA for that determination. But sort of schematically, you can see that different modules are designed to connect together. And the Gateway also, you know, it's basically the entire Artemis program. So the Gateway includes anything that touches the Gateway, like a lunar lander, or like the Orion vehicle itself, or a deep space cargo vehicle that's delivering supplies to the Gateway. And the Gateway has to also operate in different configurations, much like the International Space Station, where it starts out. It's a single module, and then over time it grows. So having a data bus configuration that can grow over time is also very important. So this is a sort of notional set of avionics. This is actually a NASA slide, give you a sense of the types of functionality that Gateway is going to have to operate with. And you can also see that different types of traffic types are also defined on this chart, with best effort, rate constrained, and time triggered. And Matt's going to kind of go through a little bit more details on what all that means. But this kind of gives you a sense of the types of functionality that has to be accommodated on the Gateway, and also that the sort of center of it is one fault-tolerant command and data handling system, of which the TTE products can support as well. So the NASA open standards could be kind of capsulized as it relates to the data bus and software into these elements: a time-triggered Ethernet data backbone. NASA specifies, or maybe specifies a little too strong, but basically likes the DIMA type of approach, distributed integrated modular avionics, which uses time-space partitioning, such as ARINC 653, to allow different functions, which can even have different levels of criticality, safety criticality, to operate on the same processor. And then also they support the CFS software infrastructure for the basic type of infrastructure for software. And the advantages of this is lower mass for cable harness. With a switch-based system and high data rates, you're really going to cut down on the point-to-point wiring and the overall cable harness mass. In fact, this is an older system, but it's public knowledge that the International Space Station has more than 120 mil-standard 1553 buses. So if you don't use a technology like this, you can end up having to have lanes of criticality on top of additional lanes for redundancy. And it really adds up on the number of data buses and the cable harness mass. And then by having time-space partitioning such that you can put different functionalities on fewer numbers of computers, you save mass and performance there. Also, this gateway system is unmanned for 11 months out of the year, so automation is a really big deal, and maintainability is a really big deal because it's probably going to have a lifetime of 15 years or more. So, we as a company support NASA's vision for the gateway with these types of features. I'd say the only sort of trade-off for getting these advantages using time-triggered Ethernet is you do have to schedule the network. It's an extra piece of work. You put a little bit more work in up front, and it pays dividends in the fault tolerance aspects and the operation of the network itself. So, Matt, over to you.
All right, thanks, Bob. So Bob talked about TTE Ethernet and some of the advantages of using it, but over the next few slides I'll talk about how it works and what the principles are behind it. So TTE Ethernet allows for the use of 3 different traffic classes. There's the basic IEEE 802.3 Ethernet, also referred to as best effort Ethernet. This comes with no performance guarantees at all. But then a step above that is ARINC 664 Part 7, which is rate constrained. Basically, the amount of data that is sent out in a given length of time is restricted. So this is still asynchronous, just like best effort Ethernet, but it does give you a lower jitter and a latency of somewhere between 1 and 10 milliseconds. But then another step above that is the SAE 6802 time-triggered Ethernet, which is the big advantage of TTE Ethernet. This is synchronous deterministic Ethernet. Like Bob said, it's scheduled ahead of time, so it's all completely planned out from the start. This allows for very low jitter, below 1 millisecond, and it's a known latency because you know when data is going to be sent and when data is going to be received as well. So on the bottom of this slide, you can see 4 different base periods of, this is the schedule of Enet system sending different frames of data throughout the network, and the gray time-triggered boxes are scheduled ahead of time. And what happens with the best effort and rate-constrained data is those are used to fill in the gaps whenever scheduled data isn't being sent. So one way I find helpful to explain the concept of time-triggered Ethernet is comparing time-triggered and event-triggered and an analogy of transportation instead of data on a network. So we all know cars and taxis, and they're event-triggered because they travel whenever they're needed. You can just hop in a car and decide to go, and it goes then. So the advantage there is it's flexible. But the disadvantage of using a car is what you can see on the right. You might run into a traffic jam because maybe everyone wants to use the network at the same time, or the road. So this is where time-triggered comes in. They are not event-triggered, it's time-triggered. So trains and subways operate according to a fixed schedule. They all agree on what the current time is, and they all have their own agreed upon schedule. And due to this, it's very predictable. When you hop on a train, you know when you're going to leave one station and when you're going to arrive in another one, or at least it's supposed to be predictable. So deterministic Ethernet is this time-triggered example, more like trains and subways than cars and taxis. So now you can see This is an example of a piece of time-triggered data flowing through a network from the end system on the left to the two end systems on the right. You can see 4 of these nodes. You have an end system, then 2 switches, and then 2 end systems on the side. And 4 of them are time-triggered. These are the blue ones with a clock, and 1 is not time-triggered. And each time-triggered node has its own version of a schedule. So on the left, it wants to transmit M at 10:45. So all it needs to do is transmit M at 10:45. And the first switch it runs into says, I will only accept M between 10:40 and 10:50 because it's scheduled to receive it sometime immediately after it's transmitted from the first end system. So it has a receive window and not an exact time, but it's still highly scheduled. And the schedule carries forward going from that switch to the next switch and the next switch to the time-triggered end system. There's always a plan for what time it's going to be transferred and what time it's going to be received by a switch or an end system. And we also have the non-time-triggered end system in this example. It can be a part of the network, but it's not, it doesn't take part in time-triggered communication. So it just receives that frame M whenever it comes. It doesn't have a receive window. All right. So I talked about the need to plan the network ahead of time. You need to figure out basically the network setup and what kind of traffic you want on it. So TT Tech provides a suite of TTEthernet development tools. These are essential software tools for the design and configuration of TTEthernet and AFDX networks. So when you plan your network, you're going to use TTE plan, and you can put in switches and systems, different cables, redundancies. You can specify what kind of traffic, whether time-triggered, best effort, or rate-constrained is going to be on the network. And then using TTE plan, you get a network configuration out of that. And then TTE build separates that out into device configurations. And device configurations are loaded onto your network, the switches and the end systems, using the TFTP loader there. And you can see we also have tools like TTE verify and TTE analyze. These are independent verification tools, and you can perform network analysis just to ensure the network is behaving as you specified at the start. Okay, so once you've planned the network and you've created those device configurations, what are you going to be loading them onto? So these are the TTE controllers for space. You can see on the left, there's the TTE end system controller, and on the right is the TTE switch controller. And they look exactly the same because the hardware is the same. The only difference is the firmware loaded onto them. But there are 2 different versions. There's the space grade ceramic package and the high-rel plastic package. TT Tech recommends use of high-rel plastic for early development and testing, and then moving on to the space grade ceramic package for advanced testing and in-flight use. Okay, moving up from the controller to the card level, this is the TTEthernet platform for outer space. On the left and in the middle, there's the TTE switch space CPCI card and the end system space CPCI card. The switch contains 12 Ethernet ports, 6 gig speed, 600 megabit speed, and the end system contains 3 gig speed. They're all IASIS compliant, and you can see the low weights there of 600 grams for the switch, 400 grams for the end system, and they use low power as well. And then on the right is the Avionics hosting unit, where the cards can slot in. There's 4 CPCI card slots, as well as a processor, where TT Tech recommends the use of AITech, what was it called? Yeah, AITech SP0 for the processor, but really whichever one meets your needs, you can use. And that one also comes with a low weight and provides power for the cards. And moving on to the development level, Bob will take back over.
Yeah, so I'll kind of finish up, but you can see we're developing a whole suite of not only space hardware, things that could be on the gateway or could be inside a lunar lander or whatever, but I want to spend a little bit of time on the development tools as well. And of course, really the prime contractors for those systems are going to make the sort of final decision on what tools and what processors and what configuration ends up. But we want to emphasize that based on experience that comes through from the airplane industry and other things, we can, I think, help the primes have the most smooth approach to software development. So here's an example of a development system that we've had around for quite a while, and these are shipping all the time, that has multiple switches and multiple end systems, and it has essentially the ASIC, the plastic ASIC, inside these PCs for tying into the time-triggered Ethernet network. And this operates with Linux as the operating system, and this is what we would suggest that you start with. And more specifically, for Gateway, we would want to introduce CFS into the mix as well. So you'd start with this development system that I showed in the previous chart, and you would have CFS sitting on top of Linux, and then that is talking to an end system, and then that ties into the switch, and you'll have a sort of mini network right there operating. You use this environment to start with because it's the lowest cost. It's sort of the easiest to deal with Linux. A large number of software engineers understand Linux very well. They're easier to find and stuff. And you would develop your apps for CFS in this environment. You can also exercise basic sending data to the network and getting data back, get all that up and running. And if timing is important to you, there's also some middleware that we can provide that ties the CFS scheduler to the time-triggered Ethernet clock. Because again, we didn't really harp on it too much, but the other big piece of this whole network is there's network time that's distributed to all the nodes, and there's a methodology when you bring two networks together to decide, do they stay separate in from a timing point of view, or is one considered a higher priority than another, and so the lower priority will synchronize to the higher priority. So in this environment, you can be tied to time-triggered Ethernet time and be running on your CFS app and get started. But for the actual flight system, we think it's important to move into a more robust RTOS situation. So again, we're recommending a time-space partitioned operating system that CFS would sit on top of or inside of partition. And our company's got the most experience with ARINC 653 because that's a standard for the airline or airframe, civil airframe industry, and there's a lot of certification work already done on that. You could also use other time-space partitioned operating systems. It would work just as well. So moving from that other setup to a setup that has like a VxWorks 653 or something like that, then you can get into actual hardware in the loop types of simulations, a verification process, and ready for flight aspect. Also, for Gateway in particular, there's a whole nother additional verification that goes on the tail end of that, which involves NASA hardware. And without spending a lot of time on it, NASA's building a complete verification facility for the Gateway, similar to what they have today with ISS, where if you have a new flight system, you can plug your flight system into the ISS simulator and make sure it all works. The same thing will happen with Gateway, where you'll be able to plug your, let's say, lunar lander simulation or actual real flight hardware into the Gateway simulator and go through final verification process that way. So this two-step process has been tried out on real flight programs under the Next Step program that NASA has funded. It worked really well, And, you know, even you can have multiple contractors that come together and each person puts their CFS version into a different partition. Worked really well. And last point, the time-triggered Ethernet drivers for using 653 tie a partition timing to the network timing. So in a multi-processor environment, each one is running their own operating system, but their partitions where their fundamental software is running are tied to the network time and therefore can be compared to each other for fault tolerance reasons. And it all works out great. So anyway, that's kind of a real top-level view of how we would recommend that you would do a software development for Gateway. It's a cool thing. It's a national priority, and we're very proud to be part of it, and hopefully provide some good solutions for NASA and the nation. Any questions?
One back here.
So I get that TTE is all about time sync and all that fun stuff. Do you provide ability to sync from an external source, say like GPS or some other source?
There's definitely ways of doing that. So we've looked at syncing the network to an absolute time, I think is what you're saying. As far as Gateway itself, you know, that's part of the discussion that's going on because there is no GPS in Cislunar, and as long as the Gateway stays self-consistent within the Gateway, you know, that's probably the most important thing, as opposed to being synchronized to an absolute source. But anyway, the answer is yes, and it's, you know, it's an architectural question that's still being discussed.
Okay. Thanks.
So you had said that Gateway needs to be reconfigurable as modules are added, but also that for time-triggered Ethernet, you need to come up with a network schedule in advance, like pre-plan it. How are those two worlds going to work together?
So it's a very good question, and basically you pre-configure the fact that there's going to be modules that are going to come in, okay? And then when they attach, they know how to, the attaching point, like the lunar lander, knows how to join the network. The other thing is, although this has to be a pre-planned network, from a maintenance point of view, this network schedule is going to be changed, you know, kind of over and over, but not on like a day-by-day basis, but more like maybe reconfigured just before a new module shows up and stuff like that. And there is a methodology for the switch to carry multiple schedules, so you can kind of load one while you're still operating on a good one, and you know, there's actually 3 schedules that each switch can carry, and a methodology to switch between them. So that you know, your concern has been handled by the network, and it definitely will work.
We can answer one more question.
You mentioned support for VxWorks. Do you also support RTIMs or other RTOSs?
Not so far, but you know, we're sort of a merchant supplier, so there's definitely discussion on different operating systems, and you know, the Europeans are going to be getting into this as well. They have a European module called the IHAB, and I know there's a lot of discussion on what operating system they want to use, and so just come and talk to us. I'd say in general, sort of the final thing, get off the stage here, is we have several of our engineers and management from Vienna, Austria, the home office. We have our local U.S. people as well. We're going to be here for another couple of days. Please stop by, find us, and be happy to talk about any of these little issues. And we're also interested in things just like what you brought up. Well, this type of operating system or this type of middleware is really important to me. How do I get a driver for it, or something like that?
Great, thank you.
All right, thank you.
Thank you very much.
All right.